Hi, everyone. Okay, so Niels Bohr, one of the founding fathers of quantum mechanics, says that if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. And we see here a picture of Niels Bohr together with Albert Einstein in those early days of quantum mechanics. And for Einstein himself, actually, quantum mechanics was so profoundly shocking that, that he actually had a hard time accepting it. But shocking as it is, we now know that quantum mechanics is the most precise theory of nature ever invented. So one of the more interesting questions that were asked in the last several decades was, can we use this? Can we take advantage of this strange quantum world and make it work for us? Can we build computers that are based on quantum mechanics, and can they perform better than our regular computers, classical computers? So the most well-known example for the potential of a quantum computer is the RSA problem. So RSA is the most commonly used encryption protocol on the internet. It's the encryption protocol that we all use to secure our money, our information. Basically, a lot of what we do online is secured by the RSA. And the RSA is based on a very hard mathematical problem. Yeah? It's based on the idea that it's hard to break down a large number to its prime factors. So it's very hard for classical computers. Even a supercomputer, a huge supercomputer, the most powerful computer on Earth, in order to crack a 2048-bit RSA encryption key would have to spend billions of years to do this problem, okay? So this is impractical. A quantum computer could do it in less than an hour. So, of course, in order to build such computers, there's a lot of development that needs to be done. You'd need to have millions of qubits. We'll talk about this, and very fast operations on those qubits. But this is something which is quite imaginable given the progress of quantum computing in the last several decades. And this computer would be, I don't know, maybe the size of this room, and it wouldn't cost too much. So it's something that we can imagine. And so we see that there is this big fundamental difference between quantum computers and classical computers. And this big fundamental difference does not lie in the materials that we use to build these devices, or in the size of the components of these devices, or in the architecture of the computer. The difference is in the very basic principles of nature. It's in the very basic rules of the game. So you know, Richard Feynman, one of the most famous physicists of all times, used to describe the work of a physicist by watching a big game of chess, and just by watching the game, just by observing the game, we ought to be able to understand the rules of the game. So if I take this analogy one step further, it's as if until about 1900 that physicists were only able to observe the pawns. They were only able to observe the very limited game of the pawns, and therefore they concluded the laws of classical physics, classical Newtonian mechanics. But in the beginning of the 20th century, physicists started to discover completely new and different chess parts, like the rook, the bishop, and the queen, and this led to the understanding of a completely new and different set of rules, which is known as quantum mechanics. So, okay, what does this have to do with computers? Yeah. Well, we continue with Feynman for just a little bit longer, because in the early 80s, Feynman starts to become interested in computers and what they can or cannot do. And he realizes that classical computers, or modern computers, are still based on classical Newtonian physics, on classical Newtonian mechanics. And he realizes that by being such, they'll never be able to achieve the richness of the quantum world. So actually, Feynman was interested in how well classical computers could simulate quantum mechanical systems. And he found out that they'll be very bad at this. They'll have a hard time simulating quantum systems. But Feynman didn't stop there. He continued to argue. He continued to argue that perhaps a machine which is based on quantum mechanics, aka a quantum computer, would be able to do much better. So he proposes this idea of a quantum computer. But in what sense this quantum computer would do better? What's the analog of the queen being able to run all over the chessboard while the little pawns play only one step at a time? Well, to understand this, we first need to look at regular computers, at classical computers. And classical computers, no matter which one, from the early computers that, from the machine that Alan Turing built in the 1940s in order to crack the Enigma code, all the way to the most powerful supercomputers that we have today, all of these computers are in some sense equivalent. They are all equivalent to a Turing machine. So a Turing machine is a machine which runs along a long strip of zeros and ones, and at every point along the way, it reads the number 0 or 1, and then it has a program which tells it what to do next. It tells it first it tells it what to write instead of this 0 or 1. It tells it where to go it tells it where to go. No, okay. It tells it where to go next on the strip, left or right on the strip, and it also tells it which command to execute next. So for example, here it reads the number 1, and then according to this number, the program says write a 0 instead, move to the right, to the next number on the right, and go to command C. So this is a Turing machine, and all of our computers are just equivalent to this Turing machine. So they're basically just very, very fast Turing machines that are manipulating these zeros and ones very, very quickly. And the reason they became so good at it, the reason why computers became so fast and penetrated, every single aspect of our life and have become an essential part of them, is basically Moore's law. This amazing prediction by Gordon Moore, one of the founders of Intel, that we're going to double our computing power every 2 years. And we're doubling our computing power by doubling the number of transistors on a single computer chip. So this is the transistor. This is the basic building block of a modern computer. And it's basically the little black box which holds the zeros and ones of the Turing machine. And so what it is it's actually a tiny electronic switch. So you see it has 3 legs here. It has the left, middle, and right legs. And it's a tiny electronic switch that can either connect between the left and right legs, like in this image here, or disconnect the left and right legs. And there is the middle leg here, which is called the gate electrode. This is used to control the switch. So by putting an electrical voltage on the gate electrode, we can open and close the switch. And this is how we represent zeros and ones on modern computers, and this is how we manipulate them. And the transistor really pushed forward classical computers, really pushed computers forward because it's relatively easy to shrink. It's relatively easy to make the transistor smaller. So let's look a little bit inside the transistor. So you cannot see here very well, but you cannot see at all for some reason. But okay, if you look inside the transistor, you find a piece of silicon inside the transistor. So just imagine that there is a box of a silicon here. And silicon is very unique. It's a semiconductor, okay, which means that it can either be a conductor or it can be an insulator. And we can affect this. We can affect this by putting a small piece of metal on the surface of the silicon, and by changing the electrical voltage on the on this piece of metal. And this is called the gate electrode. This is this middle leg right here. So it's connected to this piece of metal on the surface of the silicon. And by putting an electrical voltage on it, this electrical voltage affects the silicon and makes it conducting. So yeah, so it makes it conducting. So, okay, we see the part of the silicon which is conducting. And we can therefore switch with the gate whether the silicon is conducting or insulating. And then we can add another 2 electrodes, the source and the drain. We call them the source and the drain. And they're connected to these left and right legs of the transistor. And so by changing the gate voltage, we can either connect the source and drain or disconnect them. So this is how this transistor works. This is the switch. So this is the basic mechanism, and in the last 50 years, the microelectronic industry has developed amazing tools in order to make these things smaller and smaller, and in order to put many of these transistors on a single piece of silicon. This is called integrated circuit technology. So they put many transistors on a single piece of silicon, and they make the transistors smaller and smaller and smaller. Basically, they make the gate size smaller. Every couple of years, they make it half of its size. And this is possible because the transistor is just a piece of material. So if you make the gate size smaller, below the gate there is still just silicon. So you can make it smaller and it would still behave as this great electronic switch, like as this semiconductor. So you can make it smaller and smaller and smaller, and this is the basic idea. You make this transistor smaller up to a point in which we can fit billions of transistors on a modern computer chip. Okay, and you can ask, does this have a limit? When does this stop? Where can we not make a silicon transistor smaller anymore? And the answer, at least the fundamental answer, is that we cannot make a silicon transistor which is smaller than the size of a single atom of silicon. So this is the fundamental limit, the atomic limit. Even if you could cut a single atom of silicon, it would not behave as silicon anymore. It would not be this electronic switch anymore, and we could not make a transistor. So we are not there yet. There's still some way to go. Current transistors have a gate size which is about few tens of nanometers. Few tens of atoms. And so we're not there yet, but you see that we are quite close. There are a few more iterations of Moore's law, and we're there. And in fact, already at these sizes, already at this size of the current transistors, there are already some very problematic issues. In fact, quantum mechanics, there are quantum mechanical effects that start to interfere with the normal behavior of the transistor. So you see, quantum mechanics is already here. It's already here whether we like it or not. It's already making trouble for the microelectronic industry. But in any case, we're not far away also from the fundamental atomic limit size. So we cannot just keep on cramping more zeros and ones on the same silicon piece. And we need to come up with new ways, we need to come up with new technologies if you want to continue to increase computing power. And even if we continue to increase computing power, even if we continue to double our computing power every 2 years for another 100 years, there would still be problems that are just too difficult for classical computers. There would still be problems that are just fundamentally too difficult for classical computers to solve. So computer scientists and mathematicians divide problems according to how difficult they are. These are called complexity classes. And there are two important complexity classes called P and NP. So problems in P are problems that, loosely speaking, we can solve quite easily. P stands for polynomial time, which means that we can solve such problems, a Turing machine can solve such problems in a time which scales polynomially with the size of the problem. So an example is multiplying two numbers. So of course it's easy to multiply two small numbers, like 3 times 5 equals 15, but the idea here is that even if we make larger and larger numbers, the time that it would take a Turing machine, a classical computer, to solve the problem does not grow too fast. It grows like the size of the number or the size of the number square, so something polynomial like this. Now NP is more general, and it only requires that we'll be able to check a specific given solution to the problem in a time which scales polynomially in the size of the problem. So an example for this would be the factorization problem, the problem that I told you that stands behind the RSA encryption. So you can see that it's quite easy to verify a specific solution given two numbers that can possibly solve this problem. You could verify whether it's the right solution or not just by multiplying the two numbers and check if you have the right answer. And we said that multiplying two numbers is a P problem, and therefore verifying a solution to the factorization problem is a P problem, which makes the factorization problem an NP problem. Now, it's generally believed that P is not equal to NP. This is actually not yet proven. This is one of these big unsolved questions in mathematics and computer science, so nobody was able to show that, but it's generally believed to be the case. So we think that there are problems that can be checked easily but cannot be solved easily. And these would be problems that a Turing machine would need an exponential amount of time in the size of a problem in order to solve the problem. So for example, the factorization problem is conjectured to be such a problem, so nobody until today was able to find an efficient algorithm that can find the prime factors of a number in a time which scales polynomially with the size of the number. And this is really cool because remember at the beginning I told you that a quantum computer could do it much faster, and in fact it could do it in a time which is polynomial in the size of the problem. So this means if indeed the factorization problem is an NP problem, which is not a P problem, that means that a quantum computer could really give an exponential speed up for some of the most difficult problems out there. So, and also even just from a more practical point of view, even problems that scale polynomially, if the solution scales like n squared, like the size of the number square, if n is really large, if we have a very large problem, this could still be a practically hard problem. So it could take a lot of time for classical computers to solve. And it turns out that quantum computers could also give some significant speed up for some of these problems. So for some of these problems, a quantum computer could do this in a time which scales linearly in the size of the problem instead of, for example, n squared. So if n is 1,000,000, we gain a factor of 1,000,000. So that's still very, very significant. Okay, so we talked about computers, classical computers, and we understand their limitations now. And we also saw that the hints that quantum mechanics is here because we just keep on making these transistors smaller. And also we saw that quantum computers, I just hinted, didn't tell you why yet, but they might be able to solve some of these very difficult problems. So we have a lot of motivation now to go and explore the quantum realm. Okay, so let's start with the concepts. So the most important concept that we have in quantum mechanics is this concept of a superposition. This is the idea that while in the classical world we have only two types of cats, an alive cat and a dead cat. In the quantum world, we can have a cat which is both dead and alive at the same time. Okay, so a cat can be dead and alive at the same time. This really happens in quantum mechanics. And I was told that at Yandex, you guys like cats a lot. And no, this is not the right presentation, maybe? I don't know. I had this image of a cat, of a boost cat, that people told me that you guys at Yandex like very much, but it doesn't appear, so we'll just continue. Okay, so anyway, we can have this cat which is both dead and alive at the same time, okay? And we call this superposition. The cat is said to be in a superposition of two states, the state of being dead and the state of being alive. Okay, so this is superposition. So while the classical bits are based on these, are based on these transistors, or the classical computers are based on these classical bits that can either be 0 or 1 at every point in time, in the quantum world, we can have things that can be both in 0 and 1 at the same time. Okay, we can have a superposition of 0 and 1. And we call everything, any system which has two states that we can denote as 0 and 1, and that behaves in this quantum mechanical manner, can be in a superposition of 0 and 1, we call it the quantum bit, or in short, we call it a qubit. Okay, so this is the qubit, and we denote the state of the qubit like this. So alpha times the 0 state plus beta times the 1 state. This is just a superposition, a linear superposition of the two states. So 0, this bracket notation denotes the states, and then these coefficients, alpha and beta, they tell us how much the qubit is in the 0 state and how much it's in the 1 state. But actually, they're a bit more complicated than this, and this is very important. They don't just tell us how much the qubit is in the 0 and the 1 state, but in fact, they are complex numbers. And this is one of those things that you just have to accept in quantum mechanics. So you can write these coefficients, alpha and beta, as a times e to the I theta and b times e to the I phi. And so these A and B actually tell us how much the qubit is in 0 and how much it is in 1. But we see that they also have these phases, okay? And this phase is one of the most fundamental things in quantum mechanics, and we just have to accept that it exists. So these coefficients of the superposition are complex numbers, okay? So remember that I told you this, and it will be important later on. Okay, now this difference between the classical bit and the qubit, the classical bit being in either 0 or 1 and the quantum bit being in 0 and 1 at the same time, becomes really important when we scale up the system. So for example, if we had two classical bits, there are already 4 combinations that they can be in, right? There is 0, 0, 0, 1, 1, 0, and 1, 1. So there are 4 combinations, and the 2 classical bits have to choose either 0, 0, or 0, 1, or 1, 0, or 1, 1. But if we had 2 qubits, we can be in a superposition of all of these 4 states now at the same time. So we can be in this superposition, which is now described by 4 complex numbers, 4 probability amplitudes, alpha, beta, gamma, delta. And just to give you a feeling of how does this scale, so we saw that if we have 2 qubits, the number of states is already 4, so we can have a superposition of 4 states. If we had 5 qubits, there are already 32 states, so we can make a superposition of 32 states all at the same time. If we had 30 qubits, only 30 qubits, the number of states is already 1 billion. Okay, so note that there are now, if we wanted to describe the state of only 30 quantum bits, we would need 1 billion complex numbers, 1 billion probability amplitudes. So you would need an order of magnitude of billions of classical bits in order to describe a system of only 30 qubits. And now this gets really crazy, because if we had a system with only 270 qubits, the number of states is already 10 to the 80, which is the number of atoms in the universe. Okay, so in order to describe a quantum state, a small quantum state with only a small quantum system with only 270 qubits, you would need a number of classical bits, which is roughly equal to the number of atoms in the universe. That's the amount of classical information that you would need in order to describe this quantum system. So this is obviously impossible. This is one of the things that Feynman understood. He understood that you will never be able to even just describe the quantum state of a small system with classical information. Okay, but how does this help quantum computers to perform faster calculations? Well, the ability to be in all of these states at the same time allows quantum computers to multitask. So while the classical computer can only process a single sequence of zeros and ones at each point in time, and therefore it has to go sequentially over each different sequence of zeros and ones, the quantum computer can process all of the combinations of zeros and ones in parallel. Okay, it can process a superposition of many different combinations all at the same time together. Okay, so this is what's meant when people say that quantum computers could have an exponential speed up and exponential power. Okay, because there is an exponential number of these different combinations of zeros and ones, and the quantum computer could process all of them together. But this is not so. This is actually the reality is not that pretty. There is a problem with this. It doesn't work for all problems. In fact, if it worked for all problems, if we could process this exponential amount of states all at the same time and get the right answer, we could solve all NP problems at once. But this is not the case. There is a catch here, and I want to try to explain this catch. And to understand this, let's do some quantum mechanics on the bar. So, okay, yeah, I know it's late, so maybe to lighten up the atmosphere, we do some quantum mechanics on the bar. So this guy goes to a bar and he sees this girl and he obviously wants to talk to her, right? Okay, but now in the classical world, the poor guy has only one chance. If he blows it on the first sentence, the girl pours the beer over his head, right? So the guy has to think of all these pickup lines in his mind. He has to run all the possible pickup lines in his mind, and he can only choose one and probably fail. But if he had a quantum computer, well, then he could say all pickup lines all at the same time. So he could, for example, say, who's your favorite soccer player? And at the same time, he could say, I'm a quantum physicist. Okay? So this is great, right? This is like the most killer application for a quantum computer. Forget about breaking the RSA. This is much better. But there is a problem with this, okay? There is a problem with this, and it goes something like this. So the girl listens to all these pickup lines coming to her in a big superposition of pickup lines, and then she herself goes into a superposition because she thinks, wow, this is boring. Who cares about soccer players? And at the same time, she thinks, wow, a quantum physicist, let me hear more about it. Okay. All right. So good. So you see, this is not quite what we wanted, right? We didn't want a girl which is both interested and uninterested at the same time, right? We didn't buy a quantum computer for that. And actually, this gets worse. This gets even much worse, because when the money time comes at the end of the night and the guy needs to ask the girl for her number, she's only going to either give him her number or pour the beer over his head. So only one of those things is actually going to happen. And so physicists call it the measurement problem, or the collapse of the wave function. So while a quantum system can really be in many, many states, all of these states, A, B, C, D, E, F, G, all at the same time, when we measure the system, when we look at the system will collapse to only a single state, and we're only going to measure this single state. So remember that I told you about the probability amplitude. So each one of these states has a probability amplitude, right? Alpha, beta, gamma, delta. Actually, when you square these probability amplitudes, so alpha squared, beta squared, gamma squared, they tell us what's the actual probability that when we measure the state of the system, it will collapse to the corresponding state. So for example, gamma squared will tell us what, a priori, before the measurement, it will tell us what's the actual probability that when we measure the state of the system, it will collapse to the C state. But after the measurement, after we measure the system, it collapsed to the C state, and then gamma is just equal to 1. So this is the collapse of the wave function. And so it seems that we're back to square one, right? There is a 50-50% probability that the girl will give the guy her number, and there's a 50-50% probability that she will pour the beer over his head. So while a quantum computer could really process all of these combinations of zeros and ones all at the same time, at the end of the process, we also end up with a large superposition of all the possible answers. And when we measure it, we can only measure a single answer. We have no way to know that this is the right answer. But there is a way around this. There is a way around this. It doesn't work for all problems. It works for some problems, but some very important problems, like we saw before. And it goes something like this. So suppose that we had some more pickup lines in our superposition. Suppose we now have 4 pickup lines in our superposition. And again, they have these probability amplitudes, so alpha, beta, gamma, delta. And we said that these probability amplitudes are complex numbers, and I told you that this is going to be important. And this is exactly where it gets really important. Because, so complex numbers are just like vectors, right? You can imagine them as vectors. They have a magnitude and they have a direction, so they can cancel each other out, right? They can cancel or they can add together. Yeah, they can cancel or they can add together. So if we are smart enough, for some problems, it doesn't work for every problem, but for some problems, if we are smart enough, we can design a process in which, I think that this works. Yeah, it works? Okay. So for some problems, if we are smart enough, we can design a problem in which the probability amplitudes of the bad solutions to the problem cancel each other out. And the probability amplitudes of the good solution to the problems add together to make the probability of the good solution larger. And at the end of the day, we are left with only the good solution. Okay, so this process where the probability amplitudes cancel each other out or add together is called a quantum algorithm. So there is this whole new field of computer science now that needs to speak the language of quantum mechanics. So there are physicists, computer scientists, and mathematicians these days that spend their time thinking about new quantum algorithms that can solve interesting problems faster than classical algorithms. Okay, so before I tell you about some of the actual formulation of quantum computing, there's just one more concept, one more effect that I wanted to tell you about, and this is the concept of entanglement. So entanglement is one of these more mind-boggling things about quantum mechanics. And it managed to confuse many of the early days physicists developing quantum mechanics. So let's go back to the bar and let's examine the situation more carefully. So let's suppose again that we just have two superpositions in our two pickup lines in our superposition. So the guy says these two pickup lines to the girl, and we said that the girl also goes into a superposition. She's both interested and uninterested at the same time. But in fact, the guy's superposition and the girl's superposition cannot be separated anymore. We cannot view anymore the guy's superposition separately from the girl's superposition because they interacted. And this interaction between them made them a single system. So we can only view them now as a single system. Okay, and as a single system, as a couple now, they are together in a superposition of two states. The state one, in which the guy said, "Who is your favorite soccer player?" and the girl is bored. And the state two, in which the guy said, "I'm a quantum physicist," and the girl is interested. Okay, so together as a whole system, as a couple, they are now in the superposition of these kind of complicated states. And we call you call this an entangled state. The state of the girl is entangled with the state of the guy, and vice versa. You see, if we know the state of the girl, we immediately know the state of the guy as well. Okay. And this gets even weirder because at the end of the night, let's say at the end of the night, each one goes to their own house. Let's say the guy did not ask for the girl's number; he got too scared, and they go to their own homes, still in this big superposition. And the girl goes home and she sees her roommate, and her roommate now asks her how was the date. So at that point in time, her roommate effectively measures the state of the girl, right? So the girl must collapse to one of the two states. But the guy is in the other side of town, but he's entangled to the girl's state. So at that point in time, it determines immediately the state of the guy in the other side of town. Okay, so this is what's called entanglement. So even though the system is delocalized, what we call delocalized, it's separated in space, measuring the state of the system in one place would immediately determine the state of the system in the other place. Okay, so we are ready to talk about quantum computing in a little bit more formal notations. Let's take just a breath before that. Okay, so we said that we first, so quantum computing, yeah, so we need to have qubits. So a qubit is a system with two basis states, 0 and 1. And a general state of the qubit is a linear superposition of 0 and 1. So alpha times 0 plus beta times 1, where alpha and beta are the probability amplitudes, and they're complex numbers, right? We talked about this already. And I also told you that alpha squared is the actual probability that when we measure the system, it will collapse to the 0 state, and beta squared is the actual probability that it will collapse to the 1 state. So of course, alpha squared plus beta squared must be equal to 1. The total probability must be equal to 1. And there's a nice way of writing all of this in terms of linear algebra. So a qubit state will be described by a two-dimensional vector, a two-dimensional complex vector, this vector alpha beta, which is just a linear superposition of the two basis vectors, 1, 0, and 0, 1. So these are the two basis states, the two basis vectors. Okay, so we have the qubits, and we want to do something with them now. We want to do some calculation. We want to manipulate these alphas and betas. So what are the operations that we can do on a single qubit? So on a single qubit, we can just take some vector, some two-dimensional complex vector, and transform it to some other two-dimensional complex vector, right? And the only requirement is that the norm of the vector is 1, right? So the total probability is still 1. Alpha squared plus beta squared must always be 1. So these operations are described by unitary operations, right? Unitary operations are operations which preserve the norm of a vector. So we can describe all possible physical operations by a unitary transformation on this two-dimensional vector. So just a unitary matrix working on this two-dimensional vector. So an example for so these are single qubit gate operations. Okay, this is the name, single qubit gate operations. And an example for a single qubit gate operation is the Hadamard gate. So this is the unitary matrix which describes the Hadamard gate. And it's a really nice gate because you see it takes the 0 state, 1, 0, to a linear superposition, to an even superposition of 0 and 1. And it takes the 1 state, 0, 1, to also an even superposition of 0 and 1, but with a minus sign. So you can kind of see how this can help you, design quantum algorithms where the some probability amplitudes will cancel because of this minus sign, and some will add up. So this is the Hadamard. Okay, so now we want to have more qubits. So we said that if we had a system of 2 qubits, we can describe it by superposition of 4 basis states. So we can write it as a 4-dimensional complex vector. And we can ask again, what are the operations we can perform? And again, the answer would be now 4x4 unitary matrix operations. Okay, so for an example for a 2-qubit gate is the CNOT gate. So the CNOT gate it stands for controlled NOT. So what it does, it's the following. So if the control qubit, X, if the control qubit is 0, it doesn't do anything to the second qubit, to the Y qubit. But if the control qubit is 1, it will flip the second qubit. So if we feed the CNOT gate with 0, 0, the control qubit is 0, so we just end up with the 0, 0. If we feed the CNOT with 1, 0, the control qubit is 1, so it flips the second qubit, and we end up with 1, 1. So you can write this in terms of the corresponding matrices, and this all works out. But so far, these 2 examples that I gave are just classical, right? There's nothing quantum in them. So what happens if we feed the CNOT gate with a superposition? So we'll see now that the CNOT gate is our quantum entangler. It entangles qubits. So this is very similar to the guy and the girl on the bar. So you see, if we feed the control qubit with a superposition of 0 and 1, so this is just like the guy saying the 2 sentences to the girl, and the girl is listening to this. The girl is in some initial state 0. By the end of the process, we're in an entangled state, because you see, if the first qubit, the control qubit, was 0, the second qubit stayed 0. But if the control qubit was 1, the second qubit was flipped to 1. So we end up with this entangled state. We cannot separate the states of the qubits anymore. So, and you see, if we know the state of one qubit, we immediately know the state of the other qubit. So they must collapse together, yeah? There's a 50% probability that will collapse to the 0, 0 state, and 50% that it will collapse to the 1, 1. Okay, so now we can talk about a universal quantum computer. What's the most general quantum computer that we can think of? It would have some number of qubits. Let's say it has n qubits. And so it will be described by a very long vector with 2 to the n probability amplitudes, 2 to the n long vector. And then all of the operations we can do on such a system would be described by 2 to the n by 2 to the n unitary matrix operations. So these very large unitary matrices. Okay, and this would describe everything that we can do with a quantum computer with n qubits. So we might as well just define the universal quantum computer in this way. So a machine that has some number of qubits and can perform any unitary operation on these qubits. But it turns out that we can break down any unitary operation, any large unitary operation, to much smaller unitary operations. So this is the notion of a universal set of gates. So this is the notion that we can break down only with single qubit gates, okay? Only with single qubit gates, and with one single 2 qubit gates, we can build any size, any large unitary matrix, okay? So you see, I told you that we said that entanglement is going to be important, and this is one of the ways to see this, because we can just work on single qubits, provided that we have only one single entangler gate, which is the CNOT gate, and then we can form any large unitary operation on n qubits. Okay, and we can perform any quantum computation. So this is the main idea of a quantum computer. This is how a quantum algorithm would look like. So I'm not going to discuss this too much, but I just wanted you to see this. All these gates, you see a bunch of Hadamard gates and some other gates, they would all describe together some large unitary operation on this initial state. And this is the famous Grover's search algorithm. It's used to find a particular sample in a large database, and it can do it in a time which scales like square root of n, square root of the size of the database. And in fact, the most efficient classical algorithm can only do it with a time that scales like n, like the size of the database. So this is Grover's algorithm. There are many other quantum algorithms, and there are many quantum algorithms also on the way. So what are some of the applications for a quantum computer? So actually, because this is a new way of doing computations, a new way of computing, the number of applications is very large, and in fact, we don't even know yet what are all the possible applications, because there are people thinking about new algorithms all the time. But we can roughly divide the possible applications to three categories. So we have quantum cryptography, which we talked about. Then we have computational chemistry. So in fact, there is a lot of classical computing power today, which is devoted to problems in computational chemistry, problems like finding new drugs or designing new materials. And in some of these problems, the challenge is actually to simulate some quantum mechanical process, to simulate some quantum systems. This is, and classical computers have to work very hard to do this, right? This is what Feynman had in mind actually when he proposed this idea of a quantum computer, just to simulate another quantum system. And it turns out that it has some very important applications. And this is probably also the most, maybe the most natural application for a quantum computer, and probably the first applications that we're going to see for quantum computers will be to simulate other quantum systems, and this could help, finding new chemicals, finding new drugs, designing some nanomaterials, and so on. And the third category is quantum machine learning, AI, and optimization problems. And this is a very interesting and exciting category, which has been developed a lot in recent years. In recent years, there have been a lot of new algorithms, new quantum algorithms that attempt to solve some fundamental problems in machine learning faster than the most efficient classical algorithms. And so this is a really interesting category to follow right now. All right. So yes. So in the I don't know, maybe 20 minutes of the rest of the talk, I'm going to talk about how can quantum computer be built. Okay, so we know now about quantum computers and why they are so much better than classical computers, and we understand a little bit how they work, and we saw some quantum algorithms and a little bit of the applications, but how can something like this be built? And this is the really fun part. This is where it gets really crazy. Okay, so while the classical computer are based on this on these classical bits that are encoded in these silicon transistors, in quantum computing we're in these early days, so we're actually still on a race of what's going to form the qubit. So there is a race between different communities of physicists, each having their own ways of making qubits, and each having their own ways of making a quantum computer out of these qubits. So I listed here 4 of the leading platforms. There are more platforms, but I listed here 4 of the leading platforms. And I want to tell you a little bit about each one of them, just to get you a feeling of what it means to build a quantum computer and what are the challenges. So we have trapped ions, we have superconducting circuits, we have atoms in silicon, and we have topological qubits. So let's start with the first, the trapped ions. Okay, so ions are an ion is just a charged atom. So you can just think about an atom. And an atom has a tiny nucleus, which is positively charged. And around the nucleus, there is the electron circulating around. So there's the electron circulating around. But the electron can only circulate around on certain specific orbitals, okay, certain specific shells. And this is a result of quantum mechanics, because in quantum mechanics we don't describe an electron as a single point, but in fact we describe it with a function which is called the wave function, which describes the probability amplitude to find the electron anywhere in space. And when you solve the equations of quantum mechanics for this psi of r, this wave function, you find that there are only specific wave functions that are allowed for the electron inside the atom. So there's a series of only specific allowed wave functions on which the electron can live, and these are the orbitals of the atom. So we can use two of these orbitals in order to describe the 0 and 1 states of the qubit. Okay, so we can say that if the electron is in the inner orbital, in this case, the qubit is in the 0 state, and if the electron is in the outer orbital, in this case, the qubit is in the 1 state. And of course, because this electron lives in the quantum world, it can also be in a superposition of 0 and 1. But in order for this to really be the case, in order for this electron to really be in a superposition, these ions need to be isolated very well, right? We have atoms everywhere. We cannot build a quantum computer for any atom that we see. But these ions have to be very well separated from their environment. And this goes back to the measurement problem, because we said that when we measure the system, it collapses to one of the two states. And this is not particularly special to human beings interacting with the system, so actually almost anything which will interact with the system, so for example, a small particle of light or any other particle which interacts with the system can potentially make the system collapse to one of the two states, can potentially measure the system. So therefore, these ions must be very well separated from their surrounding environment. And there is a special device which is called an ion trap, which is used to trap, which uses electromagnetic fields, oscillating electromagnetic fields, in order to trap and localize ions very well in space inside a vacuum chamber. So these ions, so this thing sit in a vacuum chamber. There's oscillating electromagnetic fields between these 4 electrodes, and this way it traps these ions and localizes them very well inside this vacuum chamber. And here you see a picture from NIST of 3 actual ions that were trapped in such a device. So now each of these ions can be used as a qubit. And we want to do something with these qubits. We want to make some operations, gate operations on them. And it turns out that to do this, we can use lasers. So by shooting very, very finely tuned pulses of laser, we can perform gate operations on these ions. And we can form single gate operations, but because these ions also interact between them, they are charged ions, so they interact between them, we can use lasers to also perform 2-qubit gate operations, like the C0 gate. So we have single qubit gate operations, and we have 2-qubit gate operations, and you can use this laser to also measure the state. At the end of the algorithm, you want to measure the state, and you can initialize the state of these ions with the lasers again, and with some cameras and photodetectors, and so you can perform any kind of quantum computation on these with this system. Now, there is something very important to notice here, is that we have the quantum system, we have these ions, which are the heart of the quantum computer, they are the qubits. And then we also need to have some way to communicate with them. In this case, this is the laser. This is called the control part of the quantum computer. So there's the quantum part, and there is the part that needs to communicate with the qubits and make them do something, okay? And this is one of the main challenges of quantum computing. Because you see, on one hand, we said that these ions need to be separated, need to be isolated very well from the environment, so that nothing measures them accidentally. And in fact, it's not just about being measured. Even if something interacts with the system and doesn't measure it, doesn't make it collapse, it will still perform an unwanted gate operation. So it can flip the qubit from 0 to 1, or it can change the phase of the qubit. So these are called quantum errors. So measurement is the worst quantum error, but there are other quantum errors, and we don't want these quantum errors, so we need to isolate these qubits very well from the environment. But on the other hand, we need to somehow communicate with them. We need to couple them to something in the outside world, in this case, the laser. The control part, these laser pulses, they need to be shaped really well and they need to be timed very well. There's a lot of smart engineering that goes to this in order for them to do only what we want them to do and not to create any quantum errors. So that's why a quantum computing lab that deals with trapped ions would look something like that. So you have you see a lot of optical equipment. There's a lot of smart engineering which is involved just to control and manipulate only a small number of qubits of trapped ions. Okay, so the second platform that I wanted to mention is superconducting circuits. This is probably the leading platform today. And superconductors are really cool. So a superconductor is a metal which, when cooled down to very low temperature, starts to behave in really crazy ways. So, for example, it has no electrical resistance. For our purposes, what's interesting about superconductors is that they allow us to make large electronic circuits that effectively behave as artificial atoms. So you can make large electronic circuits from pieces of aluminum. Aluminum is a superconductor. And these large circuits would effectively behave like a single atom, like an artificial atom. So basically what happens in the superconductor is that even a large piece of metal, even a large piece of aluminum, when cooled down to very low temperature, would go into a single quantum state that will be described by a single wave function. So all of these electrons, a massive amount of electrons, will all behave as a single entity, as a single quantum entity with a single wave function. So this might remind you of the wave function of the electron inside the atom, only that now we have a large system which behaves like this. And this is nice because it allows you to design electronic circuits from these pieces of metal. And when you solve the equations of quantum mechanics, just like you do in the atom, you find that there are only certain allowed wave functions in which the superconductor can be. So again, these are similar to the orbitals. So again, we can use two of these in order to describe the 0 and 1 states. So this is really cool because instead of these tiny ions, we have now large electronic circuits that are made just of aluminum. So there is all this technology that was developed by the microelectronic industry. There's all this integrated circuit technology which can be used now in order to make qubits and in order to make many of them and integrate them on a single chip. So what you see here is the chip is a superconductor qubit chip used at UC Santa Barbara, now a part of Google. And so you see here some qubits. There's one qubit here, another one here, and another two here. And you also see these thicker lines that go to the edge of the sample, at the edge of the chip. And these are the control lines. These are equivalent in some sense to the laser that we saw before. So you can send RF signal, radio frequency signals, to the qubits in order to perform gate operations through these control lines. So this chip needs to be cooled down to very low temperatures. This is the cooling device, which is called a dilution refrigerator, which is used at IBM. And so the chip is going to sit right here at the bottom of this large rod, and it's going to be cooled to very low temperatures, very close to the absolute zero, temperature of a few tens of millikelvins. And it's going to be sealed and pumped, so the chip is really isolated again from the environment. And then you see all these lines, all these wirings, these crazy wirings, and this is again a part of the control system. So these lines need to be isolated very well. They need to be filtered very well. Again, because of this challenge that we need to only send the signals that we want to the qubits, and we don't want to pick up any noises from the environment on the cables or anything like that. So again, this is the challenge of the control. Okay, so the third platform is qubits in silicon. This is a really interesting platform which has gained some attention in recent years. It was developed in Australia. This field was pioneered in Australia at the Center of Quantum Computation and Communication Technology by Michel Simons and others, where they developed this ability to implant single atoms of phosphorus inside silicon lattice. So they can put a single atom of phosphorus very positioned very well inside a silicon piece. And this is nice because they kind of get the benefits of both the other platforms that I told you about. Because on the one hand, we're dealing with single atoms, right? So just like in the ions case. And atoms are really the most natural quantum system. They have really well-defined states, very sharp states, and they are also very reproducible, right? You take an atom of phosphorus anywhere in the world, it will behave the same. You can take it from another planet, it doesn't matter, it will just be the same qubit. So they're very reproducible. And on the other hand, you have all these, again, this is done on a single piece of silicon. So you have all these techniques to put complicated circuits around these qubits and integrate many qubits on a single chip. So it's a very interesting platform to follow, and it's been developed a lot in the last few years. And the last platform that I wanted to tell you about is called Topological qubits, and this is also the field that my research is in at the Weizmann Institute in Israel. This is based on the idea that we can engineer some exotic physical systems where there are new kind of particles. They're actually effective particles. They're not actual particles. We call them quasi-particles. And they are called Majorana fermions. So here you see 4 Majorana fermions. These are Majorana fermions that I made in PowerPoint, not real ones. But these Majorana fermions have a special property that they go into a quantum state which is very well protected from the interference of the environment. So actually, in order to change their quantum state, you would have to braid them. You would have to either switch their positions or circle one Majorana fermion around the other. So you have to do this very kind of extreme thing, like twisting a whole particle around another, and so if something happens locally, if some interference happens locally, something from the environment interacts with the system locally, the system will not collapse, and there won't be any error. It will just stay in the same state. So even if the Majorana fermion shakes a little bit, it just stays in the same state. And these are not easy to make. These are actually quite difficult to make. And in recent years, there have been a lot of evidence that such Majorana fermions can exist in devices that look like this. So what you see here is a device which is called hybrid semiconductor superconductor device. So you see there is a very tiny nanowire, which is made from a semiconducting material, from indium arsenide. And on top of this nanowire, you see again the superconductor. This is just aluminum. In such devices where aluminum is combined, or when a superconductor is combined with nanowires made of semiconductor, under certain conditions, these Majorana fermions emerge at the ends of the system of the superconductor. So in recent years, there have been a lot of suggestions how a quantum computer could be built from Majorana fermions. It's still in the early development, so there aren't any working qubits like in the other platforms. But there is a lot of prospects because these things have this very deep topological protection, and it's very hard to measure them or very hard to interfere with their quantum states. All right, so we have our quantum computer. This is a high-level depiction of a quantum computer. We see here the layers that such a thing would have. So we saw the physical qubits right here at the bottom. These are the heart of the quantum computer, where all the quantumness happens. And then we have the quantum control layer, which talks with the qubits, which makes them perform some operations. And then at the top, we have quantum algorithms, which solve some interesting problems faster than classical algorithms. Okay, so let me wrap it up with saying that I think that this has to be one of the most interesting fields to be in and to follow, because it really combines all these disciplines. It combines computer science, electrical engineering, and quantum physics, of course, and it really pushes the limits in all of these fields. So the technologies that need to be developed in order to build a large-scale quantum computer in the future are undoubtedly going to push technologies to new limits in all of these disciplines. And this starts to happen really fast now because this field is going through a transition. It goes through a transition from the world of academia and being the physicist niche into the world of the industry, into the big water of the industry. So there's a lot of money in recent years that is going to quantum computing. Many of the tech giants are in the game. There's many startups that were founded in recent years. And so there's all this money and all these people going into quantum computing, and this field starts to really progress fast. So I think that, I hope so, that in the next few years we're going to see a real quantum leap, a real quantum jump in the field of quantum computing. And with that, thank you.
Hello, my name is Vitaly. Can you please give a couple examples of startups in quantum computing?
Yeah,
so
sure.
What is it?
Sure. So there's a very interesting startup which is called Rigetti Computing. I think they raised like something like $70 million in the last few years, and they're trying to build a full stack quantum computer. So this is a startup which aims to the sky, right? Like really trying to build a full stack, like with all of these layers. And then there are startups that that do only a specific thing. So there would be startups that are developing some software for a quantum computer, or some electronics for quantum computers. And there are many professors now that have research groups. That come out from the academia and start their own companies. So there's a startup called IonQ, which uses these trapped ions, and they also raised, I think, just in the last year, $20 million or something like that. So there are some nice startups. So IonQ is one to follow. Rigetti, one qubit is another interesting startup.
And one more question. Do you really believe that in 2 years we will have something that we can use? Because for now, what you describe, it's awesome, but it looks like some fantastic, I don't know, some science fiction, something like from far future. Do you believe really in 2 years?
So that's a good question. So I think so. I think that some things are going to come up in the next few years. So it looks like science fiction, but in fact, there are already working quantum computers, small ones. They still don't do very useful things. So, for example, you can log onto IBM's website, and you can. They have a quantum computer on the cloud. You can connect to it on the cloud. It has 16 qubits, if I remember correctly, and you can run algorithms. You can actually, put the Hadamards in the gates and run some algorithms. Other interesting things to follow is this year Google plans to prove quantum supremacy. So this is the idea that they want to design a chip with 49 qubits that will be able to perform a certain algorithm, a certain task, faster than any classical computer on Earth. Okay, so this is hopefully going to happen this year at some point, which means, so this is still not a very useful problem to solve, but it will prove that the quantum computer could really solve some problem much faster than any supercomputer. And just think about it, it's going to be a computer with 49 qubits, only 49 qubits, faster than any supercomputer that.
Will it be big?
there is,
So I mean that can we in future have some CPU with embedded maybe quantum part or whatever? So like GPU and CPU, like CPU and quantum.
like you mean in your house? So
Yeah.
I don't know if a quantum computer will be in our
Small.
houses anytime soon, but I think that cloud computing combined with quantum computing could really be great. So so these quantum chips that have 50 qubits, IBM also just came out with a chip like that. Can sit down in these refrigerators. So one of the problems is that the refrigerator system is pretty large. That's one of the and it's pretty expensive. But it can sit somewhere else on Earth, cool down to very low temperature, with all the engineering that goes into it, and it could provide computation power, anywhere else through the cloud. So that's the hope.
That's awesome. Thank you.
Thank you very much. I've got two questions. First, when you were mentioning that quantum qubits, they are taking multiple inputs and producing multiple outputs, if I got it right.
Mm-hmm.
And in a way I got it, you mentioned that the system collapses to a single answer. Two questions. First, collapse sounds like something bad for me. Is it so? Or it's just a word that used to use in quantum computers?
It's basically the word which we use. The collapse of the wave function is indeed one of the stranger things in quantum mechanics. There is another way to view the collapse of the wave function, which is this idea of parallel universes. Okay.
Come again?
This idea of parallel universes. So you see,
of the universe?
parallel universes.
Parallel, okay.
So you see, you can view the measurement process as really making the system collapsing. But you can also, in a different interpretation of quantum mechanics, and this is more philosophical, view than a real mathematical issue. You can view it as if you measured it, and in your own, in your own universe, you measured it in the zero state, but there is a parallel universe. So now the universe is in a superposition of you seeing the qubit in the zero state. And in parallel, there is a universe in which you saw the qubit in the one state. Okay.
And the way of getting a proper answer is the quantum algorithms, right?
Sorry?
In a way, I got it. That quantum algorithms is something that is used to get a kind of proper answer from these superpositions. So it's when people learn how to get a proper or correct answer from those multiple answers. Is it?
Right. So the idea is that if you design the quantum algorithm correctly, you end up with a superposition of many answers, but where all the probability amplitudes of the wrong answers are zero. So in fact, you end up with only one state, which is the correct state.
And how do you know that it is correct?
So for some problems, there is these structures. For example, the Shor's algorithm. So Shor was smart enough to realize that there is some inner structure to the problem in which you can design, a process in which throughout the process, the probability amplitudes of the wrong solutions to the problem will cancel each other out. Mm-hmm. And you actually end up with only the right answers. This is the heart of the quantum algorithm. Yeah. So you have to see some examples for how this works in order to really get the because it's a bit different for each algorithm. Yeah, it would be a different trick for different algorithms.
Right.
Yeah.
Okay. And the second question is, what about software development for the quantum computer? How it's supposed to happen?
So there are people doing this. So Microsoft has done a lot of work in this respect. You wanna design some maybe higher level language that you will be able to write algorithms, quantum algorithms with. There are people working on this. I don't know if this answers the question.
Well, probably my question is bit too wide. What I'm trying to understand is that considering that in a couple of years, or in 5 years, in X years, we'll have quantum computers widespread in one way or another, we will have to program it and to write the programs. And after some time, it should get more and more widespread. And so it could, I'm just trying probably to understand where it could go, what kind of software would be required and make sense to run a quantum computers, and how it could happen. Probably it's like, can you tell me your prediction on how this software would be developed and in what kind of areas? I don't know how to structure this well.
Yeah, so I don't know if this would answer your question. And in fact, my research field is more in this area than in the area at the top there. But so you see, you need all these layers. So you have the qubits, and there is a way to talk to them. And then above that, you have the control layer. So you can think that maybe the control layer would have some some kind of an assembly language, which you can translate to actual quantum operations that will be performed on the qubits. And then you would need to make, some higher level language that you'll be able to compile to this assembly language and run your algorithms. And then you need to write the correct algorithms to solve your problems, whatever it is.
Okay, then I would say like any startups creating software for the quantum computers.
I think there are a few. I don't remember their names right now, but I think there are a few. Yeah, and also for example, I think Rigetti. So they're building the whole thing, but I think they're also building the software part. So yeah.
Okay, thank you very much.
Sure. Yeah.
Thank you for lecture. Some theoretical question. You said when you measure a variable observable, the wave function is collapsing. So as far as I know, if you can construct observable using over-complete vector system.
Sorry?
Over-complete vector system, and perform so-called quantum tomography state quantum state tomography operation. So can it help to avoid problems that with quantum algorithms when?
So I'm not 100% sure I understood the question. Can you maybe?
So there is operation quantum state tomography.
Right. So quantum state tomography, allows you to measure. Actually, by doing many measurements on a system which is prepared again and again in the same state, you could find the alphas and betas, for example. You could actually find how the quantum state looked like, but in order to do that, you'd need to do many measurements.
You have to have a lot of copies
right,
of the state.
Right.
Okay.
But when you actually measure, it always collapses. There are weak measurements, so you can measure. There are weak measurements that you can use to gain some information, and this is okay. So, for example, for quantum error corrections, you can do some measurements which won't make the qubits collapse, but will give you some information about what kind of quantum errors happened. And this is actually very important. Maybe this relates to your question. So this idea of quantum error correction is one of the most important ideas in quantum computing, because it allows you, by doing some measurements that won't necessarily make the qubits collapse, you could gain some information about the quantum errors, and you can correct these errors. And then keep your qubits okay. So for example, if you have a bit flip, so you make some redundancy in the number of qubits in order to describe a single logical qubit. You can use 3 qubits, for example, and then by measure the parity between different pairs of these 3 qubits, you can deduce whether you had a bit flip in one of these 3 qubits, and you can correct it. Okay, so and this is actually very important. And this is one of these things that people believe that will help scaling up those systems. Okay, so avoid errors.
Thank you.
As a physicist,
No.
I'm interested. Are there any benefits in trapped atoms instead of this superconductive circuits? Because it seems that it is quite difficult to treat this high vacuum and something like that.
Right. But as I said, like so some of the benefits of these ions is that they're very reproducible. So for example, for these electronic circuits, each electronic circuit is a little bit different. So you have a bit of a difference between each qubit, and so you need to calibrate, and so it's not exactly the same signals that you should send to each qubit, and that can create quantum errors. The lifetime of a qubit, which means how long a qubit can really stay in these superpositions, is actually much longer in these trapped ions than it is in the superconducting qubits. So you have a long time to perform your operations. But on the other hand, with these superconducting circuits, you can also do operations much faster than you can do in these trapped ions. So you have some benefits, you have some drawbacks in each one of those.
Okay, thank you. And second was about maybe scalability of quantum computing, because so in classical computer you can keep a lot of cheap computers and try to separate the task between them. But as I understand it, if you are trying to, for example, decompose this number into prime numbers, you have some kind of unique experiment. So if you want to decompose a big number, and then you need a large quantum computer, you can't do it in two separated quantum computers. Because
Right, this goes back to the entanglement. You have to entangle a certain number of qubits in order to perform these operations.
So is it maybe because currently this entanglement it can be transmitted over kilometers, so maybe you can entangle two separated quantum computers?
There are some thoughts of how you can. So I would call it maybe even the same quantum computer but different modules or something like this. But yeah, so for example, you might be able to build quantum chips that will sit in different refrigerators, and you can communicate. You can, entangle the state of this chip with this chip via some optical methods. There are a lot of schemes proposing to do stuff like that. So building some kind of a modular system that could be like entangled cross modules. Right. Yeah.
Thank you for the lecture. You've mentioned that only some specific problems can be solved with quantum computers. But is it some fundamental problem struggle, or we just do not know algorithm for these problems yet? And like, are quantum computers Turing complete, or there are some functions that can be computed by them that are not computable by traditional ways?
Well, so you see, okay, so you're asking whether a quantum computer can really give these speed ups, or whether it's just a matter of finding the right classical algorithms?
Well, not even speed up, but other Turing complete. So can we solve any problem with them in some probably big time?
Okay.
Does exist some fundamental limitations on problems which can be solved by a quantum computer?
Yeah. So it seems that there are, and also it seems that there are on classical computers, right? So it seems that there are NP problems which cannot be solved by classical computers in a polynomial time. But it's not proven. So nobody really knows, you see. So someone could come up tomorrow with an algorithm that solves all NP problems efficiently in a time which scales polynomially. So this is probably not the case, and there is, many people have tried to find some efficient algorithms to solve some problems that seem to be NP hard. But this is not proven yet. So it's not proven that that quantum computers could really do better, but it seems to be the case. And yeah, so I don't know. Maybe this answers the question. No.
Well,
Okay.
no, I'm asking even not about time, but if we can solve any problem from P with some with quantum computer.
I think that it always comes down to time. So the separation is in how long will it take us to solve the problem. So you can factorize large number with a classical computer. It would just take billions of years. So any such NP problems could be solved in a just very, very large, unrealistic time. So so the line is really between problems that we can solve in a reasonable time, in a polynomial time, and between problems that we don't know how to do this, and maybe there is a way. Nobody found it, but probably they would require an exponential amount of time. So a quantum computer, we see that can solve at least some of these problems in a polynomial time. At least some of these very difficult problems that nobody could solve faster, it can solve faster. So this is where it's at right now. Yeah.
Well, okay, thank you.
Okay.
So thank you for the presentation. I think we do appreciate the cats here. Yes. It was nice. You've mentioned that you're doing a project or your own research, and what are the very latest practical results of it? Is there just a level of PowerPoint presentation, or you have something else to share with us?
So my research is in this field of topological quantum computation, and it's more about basic science. So it's more about realizing these states, verifying that they have these properties, and then if they do, then maybe in the future we'll be able to build qubits from them. But at the stage that we are in, it's very much basic science. So it's not something that you could still do anything useful with. But there are schemes that propose how we can go from here, how we can use these hybrid semiconductor, superconductor devices in order to start building qubits, and this is what people are trying to do these days.
Okay, good luck then.
Okay.
Okay. So I have a very strange question. Are you not horrified by the future which the quantum computers bring? Let me explain. So you have mentioned that a 10 qubit quantum computer is roughly equivalent to 2 to the power of 10 transistors, right? So imagine you were mentioning that IBM is working on a 50 qubit computer or 49 qubit computer. That's, let's say, 5 to 6 orders of magnitude the computing power of an average computer nowadays. So imagine if the scalability problem is solved, you could possibly be able to build a 100 qubit computer. And of course, the main task for the quantum computer absolutely would be the decryption. Right? So this means that whenever someone develops such a computer, he or they have the power to destroy economies or to basically to get access to all the restricted, to all the encrypted data on Earth. So don't you think this is a problem?
Well, I think, first of all, I think we are very far from the day that quantum computers could really break practical RSA encryption. You'd need a very large-scale quantum computer. You'd need probably a few million. You need about 1 million logical qubits. So we talked about error correction before. So you use many qubits in order to build a single qubit, a single logical qubit, and you would need a lot of these logical qubits to break down current RSA encryption. So this is very far away. So it won't, like 100 qubits won't be enough, 1,000 qubits won't be enough. It will take a lot of time. And the first applications, I think, would be more in the more positive side of the equation, which is finding new drugs or finding new materials that can possibly help humankind. This is my hope. And like with all technology, I think that this is, we are progressing, we're making better and better computing machines. And the important thing is to use it for good and not for bad. But again, I think the day that we're going to actually be able to crack RSA encryption is very far away. And I don't think that this will be the application of a quantum computer, because I think that by that time we will also have quantum cryptography system. There are already quantum cryptography systems actually in the market that could encode information in such a way that even a quantum computer won't be able to crack the code.
Yes, that is true, but such systems rely on photonic crystals and stuff like that, and this is not something you could build into a personal computer or into a cell phone, right? So your
obviously
bank account,
the day someone has a large-scale quantum computer that can break RSA, might introduce a problem. But it's very far away, and I hope that there will be solutions. Yeah.
Okay, thank you.
Yeah.
Thank you for the lecture. I want to clear out some important questions. So we have a classical bit and a qubit.
Right.
And classical bit is actually a Boolean number. But the qubit is a real number. Well, a complex one, but the phase is not so important for us. But we can't measure this real number. So we can't measure the probability. We can't measure alpha or beta. So everything that we have cool in quantum computers we have because of the entangled states. So how can we get the speed up 2 times n? Well, not times 2 in the power of n. If we can't measure the probability, how can we get this speed up on all tasks? The orange guy here asked about the Turing completeness, and as I know, there are 2 types of Turing machines. A deterministic one and not deterministic one. So the NP class stands for polynomial time in the non-deterministic type of Turing machine. And as I understood, the quantum computer is not actually a non-deterministic type of a Turing machine, because it can't solve all the problems in all the NP problems in polynomial time. So quantum computer can simulate or emulate the classical one. Am I right? So we can solve P tasks, P problems.
So it seems that we can solve P problems, but we can also solve problems that are outside of P. But it doesn't seem that we can solve all NP problems. So like you said, it's a quantum computer is not a equivalent to a non-deterministic Turing machine. This would be the case if we could really, process all of these states in parallel, and in some magical way always get, the right solution. Even if not without making all these interferences between probability amplitudes. So a quantum computer is more complicated. It's more limited. It cannot. It doesn't seem to be able to at least do it. Again, nobody knows, because nobody knows even if a classical computer could maybe solve all NP complete problems. So nobody proved this yet. But it seems that quantum computers would not be able to solve, the most general NP problem. So there's this subclass called NP complete, right? The NP complete problems are problems that that if you solve one of them, you can solve all NP problems. They can be mapped to all NP problems. And these are problems that don't have this inner structure that that you can take advantage of to design the quantum algorithms. So it seems that you need to have, a special kind of problems that have some kind of an inner structure which you can take advantage of in order to design an efficient quantum algorithm.
Am I right that these advantages are the advantages of the entangled states? So, all we have is an quantum entanglement,
Right.
and not a superposition. So if we can build a computer with classical bits, but with classical bits that can be entangled.
Yeah, I don't know how you would be able to.
Me too, but we get something like quantum computer.
Maybe.
But it won't be quantum at all.
Yeah.
It may not be.
I mean, entanglement is a quantum effect. I don't see how how you could do it in the classical world. So you see, entanglement comes from the fact that you have a two-dimensional vector, and then you have a four-dimensional vector, and you can see that to write a four-dimensional vector, you cannot just write a cross product, right? For every four-dimensional vector that you would write. So you cannot write, for example, this 0, 0 plus 1, 1 state. You cannot write it as a single qubit state cross another single qubit state. Yeah? I don't know exactly what would be the equivalent of a classical computer, which is not quantum.
I only want to say that entangled states is what we have.
Sure, I mean,
and
yes.
None more. And the question is, what is the restriction? Can you formulate a restriction for NP tasks in order to understand if we can solve it quickly on the quantum computer?
I definitely can do it, because I'm more here than here. But I don't know. I mean, so the mathematicians and the computer scientists, they have some conjecture. They think that a quantum computer could be able to solve a certain set of problems. And some of them are actually outside of even NP problems, so problems that cannot even be checked in a polynomial time. But again, nobody can really prove that this is larger than the P problems. So this is not even proved for classical machines. So this is one of these big issues that you cannot even say that a classical computer is limited in the sense that maybe you will be able to solve NP problems. So again, it seems that quantum computers could solve a larger set of problems than classical computers. I think this is all we can say. But again, maybe there is a better answer from the theory side. Yeah.
Thank you.
The question is, first of all, thank you for the great lecture. The question is, are results reproducible? So, for example, you have a quantum computer and you run several experiments with the same input. Do you get the same output each time, or if you maybe, or you can get every time different result?
Yeah. So you could get in principle every time different results. So a good quantum algorithm would be based on the idea of the fact that you'd measure the probability that you would measure the right answer would be larger than 1/2, and then if you do it many times, enough times, you would get the right answer.
If we can run multiple times with the same experiments, eventually we can get the probabilities of all outputs, right?
Yes, but for a good quantum algorithm, you want the idea is that you'll be able to measure it a few times and with a large probability they get the right answer. So you wouldn't have to really extract all the other probabilities. They will be much smaller.
Okay, thank you.
Okay.
Hello, thank you for the very interesting lecture. My question is, we have currently a state-of-art algorithm, which is many algorithms are based on neural network, and in the nutshell, it is based on matrix multiplication. And what happens in the case of quantum computer? If we have suppose that we have a quantum computer, so will we need neural network algorithms, or will there be something else?
So again, the last sentence? I'm not sure.
I mean, if we have a working quantum computer, so do we still need to calculate neural networks, or is there any more efficient algorithm than that?
So it's a good. I mean, I honestly, again, this is. So I don't know too much about these quantum machine learning algorithms. I think that most of the things that people are doing there is to try to make, some algorithms like inverting a matrix, for example, in a more efficient time. But I don't think that you should be worried too much about this when developing interesting machine learning algorithms.
Matrix multiplication.
Matrix multiplication, I'm not sure. So, but there's a lot happening in this. So this is the third category of this quantum machine learning. There's a lot of algorithms, interesting algorithms that people come up with there. There might be something for matrix multiplication. I honestly, I'm not an expert on this at all. Yes.
Thank you for your presentation. And my question is in some way similar with the previous. Is there an existing machine learning algorithm designed specifically for quantum computer? And the other part of the question is, can we apply existing machine learning algorithms to the quantum computer? So I've noticed during the presentation that architecture of quantum computer is somewhere similar with the neural network. We have parallel inputs and outputs. So can we take, for example, a backpropagation algorithm and apply it as it is to the quantum computer? Or we have to change the basic principles of existing algorithms? Thank you.
So again, I'm not sure I'll be able to answer your question. Again, I think that my best answer would be that you should look into this field of quantum machine learning. There's a lot of algorithms that people come up with. I don't know most of them, but I mean, there's a lot of issues with solving, with some of these problems. So, for example, sometimes you could come up with a quantum algorithm. Again, this is just from the very limited knowledge that I have about this quantum machine learning stuff, is that there are some bottlenecks on the way. So, for example, you could have a quantum algorithm which inverts a matrix, in principle much faster. than a classical algorithm, but then just in order to load the data, in order to put all this data in a superposition, you need, again, a large amount of time. So then people start to think about new ways of solving these issues. So we're still, far away from really, first of all, from building the quantum computer that could be large enough to do this. But there's also a lot of stuff that needs to be happening on the algorithm side. This pretty much all I know about this quantum machine learning. I know it probably doesn't answer your question, but this is what I can say.
Thank you.
Okay.
Hello.
Yes.
Thanks for the lecture. It was awesome.
Where is it?
Okay. Me.
Yeah. Sorry.
Yeah, I'm here. You said that when you have two entangled particles, qubits, when you measure one of them, that it collapses and the other collapses too. Yes? Well, it's true. Yes, correct?
That what?
When you measure the state of one qubit, the qubit that entangles with that, it collapses too.
Right.
His function collapses. My question is, if this qubit that you use, it was entangled with some element or particle before you choose to use it in your computer, and someone want to measure function of this, can it collapse suddenly and you don't know why, and can it happen again?
Yeah, this is actually, you're touching on one of the main issues. So when something becomes entangled with your system from the environment, when the environment becomes entangled with your system, it kind of sucks out the quantumness from it. So it's you actually you want to avoid anything that becomes entangled with your system, because that's effectively it's measuring your system. Yeah. So yeah.
Can you know what when you choose this particle gonna be my qubit? Do you know that it's not entangled with something already? Can you?
Yeah. So what you can do is you can measure its state and see that it's in the zero state, and then you know for sure that it's in the zero state, and if it, and so that's the initializing the state. So it's in the zero state for sure. It's not it's not in some superposition. It's not entangled with something else. It's 100% probability to be in the zero state. So this is called initialization. And then you start performing your gate operations. Then you put it in the superposition, and then you entangle it to other qubits, and you hope that it won't get entangled to anything that you don't want it to get entangled to, or you do error correction very smartly.
Thank you.
Thank you very much for your presentation. My question is about how long a qubit can store its condition, and if it can store it for a long time, can we use long-term memory based on qubits, for example, to replace hard drives or flash cards with quantum hard drives?
Yeah. So with this, so it really varies from between different implementations of qubits. So with these trapped ions, it can be minutes or sometimes even more, of staying in these superpositions. With the superconducting qubits, it's much less, so hundreds of maybe microseconds or something of the order of microseconds. So. Yeah, so this probably also answers your second question of whether it would be effective for as a memory, because it does, it does leave a limited amount of time.
I see. Okay, thanks.
Thank you for the lecture, and I have one question. Whether such a law as Moore's law exists
but just maybe one more comment about this. So again, using this error correction, you might be able to 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 keep correcting errors and therefore save information, and whenever there is a whenever there's an error, correct it and then keep the system living for a very long time. So in principle you could maybe use use a quantum memory like this. Yeah.
Okay, once again. So whether such a law as Moore's law exists for quantum computers?
There is it's a good question. So first of all, you see, so every qubit that you add, you basically double the power of the computer, right? So so you can ask, are we adding another qubit every few years? And I think once I checked, so I think that in 1995 there were 2 qubits, and then nowadays you have 50 qubits, so you can divide and see what you get. So maybe, I don't know, we are now let's say 20 years later, and we scaled by 25. So it seems that this works okay. We're doubling the computing power fast enough, but hopefully this stays this way, but and actually increase, because if you want to build useful quantum computers, we would need many more qubits, so maybe a few hundreds, and we'll start to see maybe some of these computational chemistry applications, and hopefully this happens in the next few years. So this means we would need a few hundred of qubits, or maybe 100 or 200 qubits in the next few years. That would be great. That would be awesome. But the lifetime of the qubits actually increases a lot. Increased a lot during the years. So with the superconducting qubits, the lifetime has increased very, very fast in the last 10 or 15 years.
Okay, and the question: do we really have to? We really need to have more than 500 of qubits? Maybe it's enough, and
so again, depends on the application. So again, to break the RSA, you'd need much more.
Okay,
but maybe to solve some interesting problems in computational chemistry, I think maybe this would be enough. Again, this is more in the theory side. And again, you'd have to have them living for a long enough time. So either you have 500 qubits that are really, that are really protected and live for a long time, and you can make operations on them, or you do quantum error correction, and then you need many more qubits. So you need, for each logical qubit, you need, I don't know, 3 or 9 or more qubits. So it will, increase the number that we actually need to perform something useful.
Okay, thank you.
Hello, thanks for the lecture. I remember several years ago I read something about something called D-wave quantum computers,
Right.
and its authors say it is a technology which outperforms every classical computers. And of course, there were some skeptics who said it's a snake oil. Do you have something to say on that issue? Thanks.
So D-wave is interesting. D-wave is very interesting. So the D-wave system have thousands of qubits, yeah. But they don't build a universal quantum machine. They build a what's called a quantum annealer. Okay, so it cannot perform any quantum algorithm that you can think of, and it basically solves a particular problem, which can be mapped maybe to some of these optimization problems and problems in AI. So we basically you initialize the computer, you initialize the parameters of the problems, and then you let the computer go down to the ground state. And so it's kind of like finding it solves problems like finding the minimum of a function in principle faster than a classical computer because of the tunneling effect. So the tunneling effect is this effect in quantum mechanics where, if I throw a tennis ball on the wall, it will bounce back at me, right? But in quantum mechanics, I can throw a tennis ball on the wall and it will just, in some probability, will tunnel through the wall. So you probably know better than I do that there are these problems in computer science where you try to find the minima of some function, and then you can get stuck in some other local minima. And so in the quantum annealer, you would tunnel through the heel. So let's say you have like this heel, and you want to go to the real minima. And in a classical computer, you'd have to climb up the hill and then go down. It would take a lot of time, a lot of computing power. And in quantum annealers, you could tunnel through this barrier and reach the ground state, reach the actual minima faster than in classical computers. So these are the kind of problems that the D-Wave system is supposed to solve faster than classical computers. But again, it cannot do all kinds of quantum algorithms. It's only certain ones.
Of course, sounds pretty promising. And what is the speed up?
So I think these are problems that where you expect a square root speed up. So you expect to solve problems that would typically take some large some n squared time, and you would be able to solve them in a linear time and an n time. But these can also, again, be problems that are hard, so it could, turn a problem which is exponentially hard to a problem which is still exponentially hard just with a square root. So e to the power of n becomes e to the power of n over 2. So it's still exponentially difficult, but maybe for some practical problems, if n is not large enough, it could create a significant speed up. So that's the idea.
Thanks.
Thank you for your lecture. You've mentioned a quantum algorithm for searching for a substring in a string. The same algorithm in classical computing is quite intuitive. Is it intuitive in quantum computing?
No, it's not so intuitive, actually. There is one intuition about this Grover's algorithm. That maybe I could describe some of the intuition behind it. You start with an even superposition of many states, and then you flip the probability amplitude of the particular state that you're looking for. For that, you need to be provided with a function that does this. So this should be a function that that is -1 if this is the actual state, and this is the function that you're given with, because you're looking for the particular sample for which this function is let's say -1 instead of 1 for all the rest. And then so you flip the probability amplitude of the particular state that you're looking for, and then you do a reflection around the mean. Around the average, a reflection of the amplitudes, and so then all the probability amplitudes that you don't want to end up with go down a little bit, and the probability amplitude of the particular instance, the particular state that you're looking for, goes up a little bit. And then you do this again and again and again, square root of n times, and you find that the probability amplitude of the state that you're looking for is now large enough so that you can, with high enough probability, get the answer. Yeah.
Okay, thank you. But the thing that I'd like to know is this field of quantum algorithms. How old is it, and does it have some patterns in it? So if you work for a year in quantum algorithms, do these things seem more simple to you, more intuitive, and what it takes you to convert some classical algorithm into quantum algorithm to take some advantages of quantum computing?
Yeah, so I'm sure that if you go into it, it will become more intuitive with time. Again, this is a little bit. So again, I'm more in the hardware part than the algorithm part. But this field has been around since the 90s, early 90s. Some of the most important algorithms that are there, like Shor's algorithm and Gover's algorithms, started there, and so yeah, I think that you know, like you saw, it's basically linear algebra. So all of quantum mechanics is basically an exercise in linear algebra. So once you get, you know, the basic rules and you start playing with them, then it's all linear algebra, and it's just, you know, coming up with smart ways of solving problems, just like classical algorithms.
Oh, thank you.
All right.
Thanks a lot for the lecture. Sure. So, as I understand, if I measure the output, I get a random one. So, if I don't like it, I have to compute everything once again to get another one. And we don't have any possibility to save the other data.
I'm not sure I understand the question.
If I don't like my output because it's a random one, I need
it's
to...
Because it's what?
No.
Sorry? Random one. Yeah, if you don't like the output, yeah.
I have to compute once again everything.
No, yes. So the idea is that again. So let's say the way you build your quantum algorithm is in such a way that you get the right answer with 80% probability. Then you just run it a few times, and then you can say, I got the, you know, you get let's say you get 5 times the answer 5. Then you could say with a probability of 0.8 to the however number you ran the algorithm, I know the right answer. Yeah. So if the probability you start with is large enough and you do it enough times, you can say with a high certainty that you have the right answer. Right. So in a sense, this is always the case, right? You run an algorithm and there is some probability that you got the wrong answer, but yeah, there's something in quantum algorithms that is by definition for some of them, like the Grover's algorithm, that the number of times you run the algorithm defines the probability that you end up with the right answer. Yeah.
Thanks.
I have another question. Yes. So in the most of classical algorithms, non-quantum, it is not so difficult to find something that motivates them and observable in the nature. For example, neural networks or decision trees. And in the case of quantum algorithms and quantum computers, is there anything like evidence that we can observe it in nature, like maybe in human brains or something else?
You're asking if there is something else which behaves quantum?
Is there something like prototype in nature?
All of nature is quantum mechanics. Nature is quantum mechanical by definition. So the only reason we don't see this is, you know, because we are being measured effectively by the environment all the time, and perhaps there's, you know, many parallel universes that we all live in. But this is a philosophical question. But nature is quantum mechanical. So there's a lot of quantum mechanical effects that happen all the time. And there's many effects that happen due to quantum mechanics, you know. So most of the chemical bonds, for example, are based on quantum mechanics. We would not have atoms being stable if not for quantum mechanics. So the electron would not, just continue to circulate around. It would collapse into the into the nucleus. So nature is quantum mechanical. That's the basic idea that those early physicists thinking about quantum computers understood that that perhaps we ought to use this quantumness also in our computers, but there are many instances where quantum mechanics plays a role. In fact, even semiconductors, the behavior of semiconductors, the reason why these transistors work, are also based on quantum mechanics. So to understand semiconductors, you have to solve quantum mechanical equations. But in the transistors, we are not using quantum mechanics in its full glory. So we're just using the fact that we have this semiconductor, and then we use it in a classical way, just 0 and 1. So the idea of quantum computing is to really take this to the edge and use these basic effects, use the superposition, use the entanglement to perform some calculations.
And then human brain. So
I have no idea what's going on in the human brain. If there is quantum mechanics happening there, it would be amazing. It would be very interesting. Perhaps, yeah.
Very interesting. Thank you.
Yes.
Thank you for the lecture. Applause.
All right. Thank you very much.